All right, so a little bit about my background. I got my undergraduate degree at Morehead State University in Morehead, Kentucky. It is a small school in the foothills of rural Appalachia, about an hour east of Lexington, if you know where that is. Small school, great program, graduated with 5 other people, so got a lot of hands-on experience. Yeah, small department. So I did an internship, an REU, at Loyola University before my senior year in Dr. Shirelli's lab. Fell in love with it. He asked me to come back. I wanted to come back, so I applied to Loyola, got in, and it's been my home ever since. So I'm in my 4th year, hopefully out of 5, of graduate school. And my talk tonight is going to be on my research with microplastics and if they enhance the uptake of toxins in earthworms. All right, so a little bit of background about microplastics. They are commonly defined in the literature as plastic particles less than 5 millimeters in size. That varies a little bit from paper to paper, but generally speaking, they're very small. They're important because plastics are a part of our environment now. They're not going away anytime soon. We've seen places like states and cities start to ban things like plastic bags, plastic containers, because we've seen they don't decompose. So microplastics, as these macroplastics break down, are going to become more prevalent in our environment, and we need to know what damage are they doing, if any, and to what effect. There are 2 different types of microplastics. They're generated 2 different ways. You have primary microplastics, which are those that are made by us. So for instance, do you guys remember the facial scrubbers and cleansers that were banned a few years ago? They were in like Neutrogena and things like that. Those are primary microplastics. They're made for a purpose. They're abrasives, both in consumer products and also in industrial applications like concrete. Secondary microplastics are formed from the breakdown of macroplastics. So we have this giant, northeast Pacific gyre out in the ocean. It's the big garbage patch. And so you have all of these plastics in there, and either through photooxidation means, through the sunlight over time, or through mechanical processes getting caught up and torn up, that's how you generate secondary microplastics. So we do have 2 routes of how these are being introduced into the environment. And then for biological impact, that's what's being studied right now. It's a rapidly expanding field. New papers every time I hop on SciFinder, something new to read. And a lot of the studies have been done in the marine, particularly the oceanic environments. And that's because that's where a lot of the plastic is. That's where we see it. You can go out and collect kilograms of this stuff on one sampling trip. There has been a few papers where starting to look at freshwater systems. They're different. There's not as much microplastics. There's different types. So we're trying to determine in the field, is there a difference in what different organisms are being exposed to in the oceanic versus the freshwater environments. And then as far as we know, there have been no published studies of terrestrial environments, so no land-based studies. So the biological impact is being studied. We're moving from have they eaten, is there plastic in organisms, yes or no, what types is it, how much, to more of, okay, what is on it? What are these organisms being exposed to? Can we categorize it? Can we identify it? And hopefully learn a little bit more about the environment. So our specific study is to determine if polymethyl methacrylate, otherwise known as PMMA, microplastic beads facilitate the uptake of a pesticide oxidation product, Endosulfan Sulfate, in earthworms, and we're going to do the bulk of our analysis through GC-ECD. All right, so Endosulfan Sulfate is the only known toxic degradation product of the parent pesticide Endosulfan. There's a lot of research out there about Endosulfan. We know a lot about it. We know it's bad. That's why we banned it in July of 2016 here in the States, is when it was phased into effect. There's not a lot of research out there on this degradation product, which I find kind of odd. It has a longer half-life, 3 times greater of a half-life. It is just as toxic as the parent molecule. So the 2 studies I was able to find on the product said that we do know lethal concentration. It's 100 micrograms per liter in zebrafish, so it is toxic. And it is also a known neurotoxin in zebrafish. So this is not something that we want organisms exposed to. So while it was banned, you might think, oh, we don't need to be as concerned about it. You go back to the half-life. It has a long half-life. It's still persistent in the environment. And then we also have developing countries where this is not banned. It's still readily available. So we're looking at a global impact. All right, so a little bit of background about our initial study. We have 5 different soils here. We have a control soil, which is just dirt. Then we have a low spike, a concentration of Endosulfan Sulfate, and then a low spike with plastic, a high spike, and then a corresponding high spike with plastic. So we're looking at 2 different concentrations with and without plastic to see if we see any effect. The study was 21 days, and we sampled over 5 days of the experiment. So as you can see, 0, 3, 7, 14, and 21. And on each day, our collaborators took up 3 worms for analysis from each soil type. So we had a lot of dead worms at the end of the experiment. Once the worms were sacrificed and given to us from our collaborators, we needed to get that Endosulfan Sulfate out of the cells of the worms so we could see how much there was. How did we do that? Well, we had to cut our worms up into rather small pieces because we needed a surface we could work with. We need to lyse those cells open. We lysed the cells open through sonication. And our solvent, we chose dichloromethane, readily dissolves Endosulfan Sulfate. So the idea was we sonicate them, we lyse the cells, and then we pull that Endosulfan Sulfate into our solvent out of the worm tissue. Once we have that worked up, we added activated carbon as a decolorizing agent to hopefully clean up our samples. As they are biological, they can get a little messy. Then we needed to pre-concentrate our samples. We needed to make sure we could get within our limits of detection, so we just evaporated under a steady nitrogen stream. And then when we were ready for analysis, we reconstituted all of them in hexane because we needed a GC-compatible solvent. Here is the chromatography we used on the ECD. We did use a Shimazdu GC 2010 Plus. It was connected to a Shimazdu AOC 20i auto sampler. We used a Restec 60-meter column for our separations, and we had a fairly standard temperature gradient. We started off with the hold at 100 degrees, ramped up to 210 degrees, had a hold there. Then we ramped up to our final temperature, 300 degrees, with a slight hold. We couldn't really safely go above 300 due to the limits of the ECD detector. We didn't want to melt the nickel source, so we kind of pushed it as far as we could go. But with this ramp, we were able to extend our runtime to 45 minutes, so we got really nice separation. Before we did any separation, we had to generate a calibration curve, make sure we were linear within limits of detection. So we did that, and this is a sample calibration curve from my second study, which I'll talk to you about at the end of the presentation. But what we can see is we are linear in our ppm range from about 0.1 up to 5. Here I have a sample chromatogram for you. I know it's rather messy. So we have all of this coming off at the beginning of the run. And then our peak for Endosulfan Sulfate is down here, which is blown up here in B for you to see. You can see we have a nice retention time of about 35 minutes. We wanted to push that retention time, so we avoided all of this bulk here. We didn't want to get lost in all of this. And it's relatively, as you can see, calm down here. We have nice peak shape, clear peak shape, so we were really happy with our chromatography. We got our initial results last year, and they were surprising because our hypothesis going into this was the plastics, the pesticide's going to stick to the plastic, the worms are going to eat it, it's going to desorb off the plastic, and it's going to accumulate in the worm. Well, with the exception of this first batch right here, 5 out of our 6 comparisons of the soil with the plastic compared to the soil without the plastic, we actually see remarkably less, which is rather surprising to us. We didn't expect this at all based on what we saw in the literature. So we kind of had to sit down and go back to the drawing board. You know, did we mess up? Was there something wrong in our extraction procedure? Did our collaborators do everything correct? Are these really what we're supposed to be seeing? So with all of that, we sat down and we said, okay, no matter what we figure out, we need to run a second study. We need to prove that these are reproducible, and if not, you know, if we do find we made a mistake, we need to correct it and run this again. So before we could comfortably do that, we had to do 2 little side projects. The first was we had to do some soil testing. Our collaborators over in the Institute of Environmental Sustainability came to us and said, hey, we've got all this soil laying around. Can you test it, see if it's still close enough to the original concentrations that we can use it again? We're like, sure, not a problem. So their targets were about 45 milligrams of pesticide per kilogram of soil, and then 3 milligrams per kilogram for the respective high and low spikes. So we extracted all 5 soil types using a quenchers method, and we wanted to see what we would get. So we ran all of these samples on an Agilent G6460 triple quadrupole tandem MS. We used Infinity 1290 LC system, and we chose to use a selected ion monitoring scan instead of a product ion scan. We elected not to use a product ion scan, which is fairly common for tandem MS because we couldn't get the molecule to fragment. If you remember, it's a bicyclic ring. We could only really fragment off the sulfate group, so we weren't comfortable that we could generate those 3 ions that are kind of key for being able to go, yes, this is our molecule of interest. So we kind of went back to the drawing board and said, okay, maybe we can do a SIM scan. We're not going to fragment it, but we're going to look for our 3 most abundant isotopes based on those 6 chlorines that are on the molecule. So that's how we got the 418, 420, and 422.9 M over Z values. A quick refresher on how a SIM scan works, if you don't know, is your triple quad has 2 mass selectors, MS1 and MS2, and then a collision cell. So in a SIM scan, MS1 is open, so all of your ions pass through. None of them are crashing into the rods, they're continuing through the mass spec system. Our collision cell is turned off. We don't want to fragment anything. We want that parent ion for identification. And then in our third mass selector, we are flipping between radio frequencies for these 3 values. So all the other ions crash off into the rods. We're only seeing the 418, the 420, and the 422.9 ions. For our chromatography, we used an Xterra C18 column. We do have a guard column attached to help preserve the life of the column. Our phases, we had an aqueous phase of ultra-pure water, a mobile phase of methanol, both of which contained 0.25% formic acid for acid-base functionality. And then we started with a pretty standard gradient. We had already developed this for previous chlorine work in the lab, and we found that it worked, so that's what we stuck with. We start at a low percent organic phase, ramp up to 90% here, have a slight hold, and then we return back to starting conditions for a total runtime of about 35 minutes. So not too terrible. We did generate a calibration curve. This was just our preliminary calibration curve to show, yes, we do have linearity within the range we're expecting. We were pretty happy with it. And then we saw these. They weren't the best peak shape, but what we did like out of these, so in A, I have our total ion chromatogram. B, C, and D are extracted ion chromatograms for the 418.9, 420.9, and 422.9. We do see they all line up. So that means we have the same retention time. We're looking at the same molecule. We're looking at the different, labeled isotope ratios, but we are getting all of this from Endosulfan Sulfate. So that was nice, even if our chromatography wasn't the best. And our chromatography wasn't the best because we were looking at really small counts. So we went through, ran all of our soil samples, and our control gave no signal. That's great. But our low spike with plastic also gave us no signal. Not so great. Our low spike gave us such a small signal, I wasn't confident if it was a true signal, if it was noise. I didn't know what it was. I wasn't even sure it was a peak. Our high spikes, both with and without plastic, did give us nice signal, so that was good. But I was really concerned. I was just kind of like, is this on my end? Is something wrong with my quenchers method where we're not seeing what we're supposed to see? Or are these really just that degraded either through, just breakdown, oxidation breakdown of Endosulfan Sulfate? Is it because the worms have, eaten all of this? What's going on? So I decided to run some external spikes. Can I mimic the concentration I'm supposed to see? Are we close? Are we not? And go from there. I attempted to make a low spike and a high spike. My low spike was very successful, gave us a very nice signal, much greater than, quite frankly, any of the experimental soils. My high spike didn't work so well. I believe I was precipitating the Endosulfan Sulfate out of solution when I attempted to reconstitute it. So I ended up with a milky white gunk that I was not going to run through my triple quad. Didn't want to gunk up my nice clean lines. So I did only run my external low spike. And so I talked to my boss and we were just kind of, okay, then, you know, this is what it should be. Obviously it's not there. These results seem pretty solid. So we calculated our concentrations for the high spikes. Neither one of them was even a milligram per mil. Excuse me, not a milligram per mil, a milligram per kilogram. Our target was 45 milligrams per kilogram. We were way off base. We went back to our collaborators and said, yeah, there's no way. We got to make fresh. We also did a gravimetric analysis study. We wanted to figure out possibly why our samples with plastic were giving us less signal. We sat down, I went to the literature. What I saw was, hey, more and more people are looking at these things called absorption coefficients. They're looking to see how well something sticks to the surface of a microplastic. And I was like, okay, maybe that's what's going on here. Maybe we are getting the Endosulfan Sulfate from the worms. If there's microplastics still on the worm, we're lysing the cells, but rather than driving into the dichloromethane solvent, it's adsorbing onto the surface of the microplastic, and then we're not pulling it off. So we decided to do a gravimetric study to test that, to see if there was any sort of weight difference in the worms that weren't exposed to plastic versus the worms that were. Could we see any noticeable change which we would contribute to the microplastic in the worms? So we took 15 milliliter aliquots, that corresponds to about a gram of worm, of the already sonicated samples. So that means I had worm tissue and dichloromethane, and I would put them in a beaker. The beakers were pre-weighed. Chose low spike with plastic, high spike, and high spike with plastic across the different days. And I evaporated them so we could end up with just worm tissue and plastic if it was there. Dried them overnight just to be safe. Wanted to drive off any and all moisture. Then I reweighed them. And what we saw confirmed, I believe, my theory. We see that across all days, day 7, 14, and 21, there was a greater weight, which we attribute to the microplastic, in the worms that were exposed to plastic and pesticide versus the worms that were just exposed to pesticide. So we needed to account for this in our second study, because what this means is we're not just looking at worm tissue. We're looking at worm tissue plus soil and microplastic that was in the worm when they were sacrificed. These worms aren't empty, they're biological systems. They were eating up until the moment they were frozen. Well, what if I cut it open and rinse it out? Will that work? So that's what we tried. We weighed the worms before we did anything, so we would have that total mass. And then I cut them lengthwise down the middle, and I have pictures for you on the next slide to illustrate that. We rinsed all visible dirt and microplastic from the inside of the worm. We did our best to preserve any tissues, any organs that are in the head of the worm, because we wanted that worm tissue, but these things were chock full of dirt and microplastic. You could see it. I'm going, yep, that's where my pesticide's going. So then we patted them dry, weighed them again, so we would have a weight of just the worm tissue, cut them into fine pieces, and continued with our workup procedure. So if we look here, we have this nice uncut worm. Sorry for the shine, they are a little wet. And then in B, we have the worm that's been sliced open, all dirt and microplastic has been removed, and you can see we still have organs in the head and neck area, which is what we want. So rather than working up worm plus dirt, we skinned them all and worked up just worm tissue. Now there could still be very small amounts of microplastic that we didn't see, that we didn't rinse out, that were stored in the worm tissue, but compared to what was in the dirt in the worm, we greatly improved our ratio of what we're studying. So then we needed to test it. This looks great, but does it correspond to anything? So we took worms of the same replicate in the same day, so we chose day 21, because in theory, they should have the highest concentration. Rep 1, that's just the rep I grabbed out of the freezer, and we ran the two procedures against each other. And what we found made me really happy. So our skinned worm gave us a signal of 383 volts, which is about 86 parts per million. Our unskinned worm gave us a signal that fell into the noise. No comfortable decision of Endosulfan sulfate in that worm. So we saw this huge increase in signal in worms of the same day and the same replicate. We got out the microplastic, the endosulfan sulfate was no longer adhering to it, and we were driving it into solution. Solved my problem. Fantastic. Let's run it again. So that's what we did. And I have half of our preliminary results for you, which I just got a few days ago, so bear with me. What we have here is we have day 7, 14, and 21, and we're comparing the spike without plastic, that is the blue bars, versus the spike with plastic, which is the light blue bars. And then we have a concentration in milligrams per gram of worm here on our y-axis. Our low spike confirmed our initial study. We're still seeing a greater concentration, in worms without plastic than worms with. The high spike, that's true for day 7, but then we get to day 14 and 21, and we see this, I hesitate to call it exponential, but this remarkable increase between days 14 and 21 in concentration. Honestly, we're not sure what's going on there. Like I said, we only have half the picture, but the low spike is really promising. We also are going to focus in on the low spike, because this is more of an environmentally relevant concentration. When you're out in the environment, you're not just going to stick one pesticide or one hydrophobic molecule onto these microplastics. Anything that's exposed to it and hits an open surface is going to stick. So that lower concentration is really of interest as far as environmental applications are concerned. Now, I said we only have half the picture because when we talked to our collaborators, we said, hey, these worms are full of dirt and microplastic. I want to see what's on it. I want to see if what's in the worm corresponds to what is being stored long-term in the worm. Are the worms not exposed to plastic, not processing through as well? Are the beads just that saturated and then it's not coming off? The digestive tract of the worm, does it meet the desorption parameters necessary? So rather than sacrificing the worms right after collection, our collaborators stored them for 24 hours, collected any defecation they made, and then froze that and gave it to us. So it'll be interesting to see when we get the worm excrement worked up, do the trends correspond to what we see here? You know, do our worms without microplastic still have a greater concentration of pesticide in their excrement, or is it flipped? Do we see a greater concentration of pesticide in the excrement of those exposed with the plastic, meaning it is stuck to the plastic rather than get adsorbed in the worm? So for future work, I still got a lot of work to do. We have to finish running our remaining worm tissue replicates. We share time on the GC-ECD with Loyola's biodiesel lab. So I have to work around his schedule. For those of you who don't know, Loyola does sell biodiesel. So he runs a business, I do research, he gets priority. And then we need to finalize our extraction procedure for how we're going to desorb the pesticide from the microplastic in the soil that's in the worm excrement. And we have to be really careful here because our samples are so small, we don't really have replicates. We don't get a shot to do it again if we mess up. So I'm working with a lot of control soil, because that's essentially what worm excrement is soil, and going, okay, can I recover, 95 or better % of what I spike in on microplastics before I move on to the worm excrement itself? And then of course we have to analyze those. And then, like I was talking about previously, compare the two. Do the trends mirror each other? Do they not? What conclusions can we draw from this now that we have more of a whole picture rather than just half? So with that, I want to thank everybody who helped me along the way with my research. Dr. Shirley is my research advisor. He puts up with a lot of my questions and lets me tinker on instruments and all sorts of things like that. Matt, he is a former grad student who earned his PhD. He was my lab buddy, taught me the ways, let me take apart instruments, helped me understand things. Sometimes you just need that person to bounce ideas off of who understands what you're doing, so I'm very grateful for that. Dr. Wong and Ritesh are our collaborators over at IES. They did all the soil and all the worms. I just got them when they were dead, so I'm very grateful for that. And then Nick, Kat, Becca, Rachel, Brett, they were all undergrads who sonicated worms for me. That was a multi-hour process that they sat there listening to something that sounds like a dentist drill. So kudos to them for sticking it out. And then you guys for having me, and then Loyola for letting me do my graduate school research in the first place. So at this time, I'll take any questions.